Bismillahirrahmanirrahim. In the name of Allah, the most beneficent and merciful. Assalamu alaikum. My name is Dr. Rana Farhat Mahmood, and today we are going to discuss about the X-ray diffraction technique. This is our 1.6 lecture of this first chapter about X-ray diffraction technique. The course code is CHEM5134. Here we are going to discuss some application of X-rays diffraction techniques or XRD, in which we see that it can be useful in determining the material properties. It is also used as semiconductor properties on that depends on structure. We can find out these kind of semiconductor properties by using XRD techniques. Structure effect energy band gap can also be calculated by using XRD techniques. Band gap determines wavelength absorbed or emitted. It is also used to manipulate lattice structure. If we discuss the summary of the previous lectures we have studied, in which we have shown that crystallographic point, what is crystallographic point, and the direction and phase are specified in terms of the indexing schemes. Materials can be single crystal or polycrystalline. That is the material that we use to study through XRD technique. That material could be single crystal or polycrystalline materials. Material properties generally vary with single crystal orientation, that is anisotropic properties, but are generally non-directional isotropic properties in polycrystalline with randomly oriented grains. That means the single crystal orientation show anisotropic properties generally, and the material which is in polycrystalline shape, it shows non-directional or isotropic properties with randomly oriented grains. Some materials can have more than one crystalline structures. This is referred to as polymorphism or allotropy. Experimental X-ray data. This comprises of array of spots of photographic plates are on CCD. Spots having varying intensities. Intensity data is recorded on the designated HKL Miller indices. This data is depend on arrangements of atoms of the molecules or molecules in a asymmetric part of the unit cell. Problem is diffraction pattern register only the intensity of the diffracted waves. The phase problem that we face in XRD techniques. The physics of diffraction requires that in order to resolve features of atomic structure, it is necessary to employ radiation with the wavelength of the order of atomic spacing are smaller. X-rays have suitable wavelength and interact with electrons of the atoms. However, the interaction between X-ray and electron is weak, and such energetic radiation causes ionization of the constituents atoms of the molecules. The damaging of the molecules under the study occurs. These are some problems that we find in using XRD techniques. Therefore, it is necessary to examine a vast number of molecules simultaneously. This is achieved by using a crystal containing many copies of molecules in a regular lattice. Unfortunately, it is only possible to measure the amplitude of the diffraction pattern spots by experimental mean. The phase information is missing. This is the phase problem of X-ray crystallography. Without phase information, it is impossible to reconstruct the electron density of the unit cell. And the phase problem is the problem of the loss of information concerning the phase that can occur when making a physical measurements. For experimental data, we obtain structure factor, amplitude f, and note the phase angles. Following are the major methods used to obtain phase information. Number one, multiple isomorphous replacement, that is used for heavy atom methods, generally for large molecule. This method is used for large molecules generally. Second method is molecular replacement, and third is Patterson search. And the fourth method that we used here to obtain phase information is the direct methods, most used methods. Multiple isomorphous replacement methods. This is the first method that we have used. A larger structure such as protein are typically less rigid than smaller molecules. And thus, even in a crystal, there will be significant disorder between unit cell. Information about the unknown phase may be obtained by making a known change to the contents of the unit cell and measuring the effect on the diffraction pattern. In practice, this involves introducing a reactive group containing a heavy metals ions to the protein without disturbing the structure of the protein. That is, the two structures must be isomorphous since the heavy atom scatters more strongly than the rest of the atom in the structure. It is therefore usually possible to locate the heavy atoms alone by use of different by use of direct methods of Patterson methods. By use of direct methods or Patterson methods. Once the location of the heavy atoms is known, the scattering from those atoms may be calculated both in magnitude and in phase. Once the location of the heavy atom is known, the scattering from those atoms may be calculated both in magnitude and in phase. and the diffraction patterns are measured from both the native and the heavy atom crystals, and the structure factor for the two crystals are compared. If the structure factor from the heavy atoms crystal is significantly stronger than the corresponding structure factor for the native crystal, then the scattering from the heavy atom must be interfering constructively with the scattering from the rest of the crystal. Similarly, if a structure factor from the heavy atoms crystal is significantly weaker than the corresponding structure factor from the native crystal, then the scattering from the heavy atom must be interfering destructively and the phase must be offset. Second is the molecular replacement method. In this method, we see that an alternative approach to the phase problem may be used when the molecule under study is similar to another molecule whose structure is already known. In this case, the molecular replacement method allows phases to be obtained from the known structure. The molecular replacement calculation involves the solution of the rotation and the translation functions. The known molecule is first rotated in three dimensions, and for each orientation, structure factors are calculated from the model. This agreement between the calculated structure factor and the observed values from the diffraction pattern is used to identify the orientation of the known molecules that most closely matches that of the unknown molecule in the crystal. Next, the oriented model is placed at every possible position in the unit cell, and again the arrangement of the structure factor used to identify the correct translation. If the correct orientation and the translation can be identified, then the model may finally be used to calculate the phases for all the structure factors. Electron density map may then be calculated using phases from the model structure and weighted magnitude from the unknown structure. The resulting map may be explained to determine the unknown structure. There is now Patterson method. Now we will discuss this Patterson method in this slide. The structure of the small molecule may be solved even in the absence of phase information. While the phase determine the position of the peaks of electron density across the unit cell, and therefore the position of the atom, the presence of a strong diffraction spots along alone give a strong indication that features must be present with the corresponding spacing. That means when the phase determine the position of the peak of the electron density across the unit cell, then therefore the positive and the position of the atom, the presence of the strong diffraction spot alone gave a strong indication that features must be present with the corresponding spacing. Thus, the structure factor magnitude alone contain information about the spacing of atom in the structure. This information may be accessed by calculation of the Patterson function. The Patterson function is obtained by calculating a map using the squared structure factor magnitudes and all the phases set to 0. Instead of peaks at the atomic position, the Patterson map shows peaks at every position that corresponds to an interatomic vector in the structure. The Patterson function has been an effective tool for solving small molecules. However, its usefulness falls quickly as the number of atoms increases. This is another method, the direct methods for phase determination. This is the mostly used methods. This is developed by Hauptmann and Carle, who are Nobel laureates of 1985. The direct method, which estimates the initial phases and expanding phases using a triple relation, a trio of reflections in which the intensity and phase of one reflection can be explained by the other two has a triple relation. A number of initial phases are tested and selected by this method. This requires a powerful computer that must be based on obtaining phase data from diffraction intensities. This estimate initial phase and expand them by using triple relation, generally used for small molecules. For small and intermediate size molecule, the atoms are normally well ordered, and as a result, structure factor may be measured to very high diffraction angles. The high angle diffraction spots give information about finely spaced features in the unit cell. In this case, the missing phase information may be reconstructed directly from mathematical relationship between the structure factors. As the phases come directly from the observed diffraction pattern, these methods are referred to as direct methods. Phases are chosen for a few strong reflections. Then phases for other reflections are generated using phase relationship among strong reflections. Once enough once enough phases have been calculated, the electron density may be calculated and can be interpreted in terms of atomic positions. Unfortunately, the phase relationship become weaker as the number of atoms in the structure increases. Furthermore, this approach only works when data can be collected to a high resolution. The use of multi-solution method, by which a large a larger set of starting phases is chosen at random, and the calculation is repeated many times until a reasonable structure is obtained. It has allowed direct methods to solve structure of up to 2000 atoms. However, most proteins can be solved by this approach. However, most proteins cannot be solved by this approach because the structure factor cannot be measured to atomic resolution. Phase problems. The phase problem is the problem of the loss of information concerning the phase that can occur when making the physical measurements. The name comes from the field of X-ray crystallography, where the phase problem has to be solved for the determination of a structure from diffractional data. The phase problem is also met in the field of imaging and signal processing. Solution for phase problem. In X-ray crystallography, there are several ways to recover the lost phases. One is a powerful solution is the multiple wavelength anomalous dispersion, that is known as MAD method. MAD, multiple wavelength anomalous dispersion method. In this technique, atoms' inner electrons absorb X-rays of the particular wavelength and re-emit the X-rays after a delay, inducing a phase shift in all the reflections, known as the anomalous dispersion effect. What is MAD? We have studied in the previous slide. Analysis of this phase shifts result in a solution for the phases, since X-ray fluorescence technique like this one require excitation at very specific wavelength. It is necessary to use synchronous radiation when using the MAD method. Dear student, this is our second last lecture of our first chapter, that is about X-ray diffraction technique. And in the next lecture, that would probably be our last lecture for this first chapter, in which we will discuss the remaining method that we are discussing in this chapter, in this lecture. So, till then, Allah Hafiz. See you in the last lecture. Okay. Thank you very much for listening this lecture. So, have a nice time. Allah Hafiz.